In this PowerPoint, we start talking about free body diagrams for forces. So from our lab that we do in class, we see that the force is going to be equal to mass times acceleration. Now the problem with this is that it's an incomplete statement because in our lab we only dealt with one force at a time. But if we have all the forces that are acting on an object, then that's going to be equal to mass times acceleration. So what we have to do is we have to increase our equation to say that it's going to be equal to summation, which is the sigma. Summation of forces equals mass times acceleration. That's a Greek letter sigma. It equals summation, and it also means to add up all of the whatever's after it. Now it's a function just like delta is a function, which means you have to have a variable after it in order for it to be there. You can't just have sigma by itself. It's got to be sigma of something, which means you add up all of the whatever it is. So the net force, the total force, is going to be equal to mass times acceleration. So there are going to be a lot of forces that we talk about in this class. We're going to include gravity as the weight of an object, and actually weight and mass are not the same thing. Mass is the amount of matter that makes up an object, while weight is the force that gravity is applying to that mass. So the gravitational force of the Earth being applied to your mass is called your weight. We also have friction and air drag, tension, thrust, electrical forces, and magnetic forces, which we're not really going to be talking about until we get later in the year. Normal force. Now, normal force is a little bit different than what we're used to. The normal force is a force between two objects that are in contact with each other, like a box that's sitting on a table. The table and the box apply a normal force on each other. Now, the reason it's called a normal force is actually because normal is a word, a mathematical word that means perpendicular. And because that force is being applied perpendicularly to the surface, then that means that that's why we call it a normal force. And we got the strong force and the weak force, and we're never really going to be talking about strong force or weak force after this point because those are nuclear forces, and the strong force is the force that holds the nucleus of an atom together, protons and neutrons, and the weak force is actually what holds a neutron together from becoming or decaying into a proton and an electron. Now all these forces can be categorized into two categories. We call the first one contact force. A contact force is a force that only exists between two objects that are in contact with each other. For example, you wouldn't have a force of friction between two objects or air drag without having that air in contact with the object. Tension, you wouldn't have a rope sitting next to a box that would actually apply a force on the box. It would have to be connected to it. Two objects wouldn't have a normal force being applied to it unless those two objects were in physical contact with each other. Now the second category is called a field force. A field force exists between two objects just by being around each other. So gravity is a great example of this because if I jump up off of the Earth still pulls me down with a force of gravity, because it's a field force, because I don't have to be in contact with it. Electromagnetic forces, maybe you've dealt with this before. If you've ever rubbed your head with a balloon and had hair stick away from your head towards the balloon, then that's an electrical field force. And then you got magnetic forces too. Maybe you've had two magnets, one sitting on a table, another one you kind of move the other one around the first one, and it kind of moves back and forth without being in contact with it. And then you have strong and weak force that are also field forces. So gravitational force is something that we look at in this class, and this video is a great demonstration of how everything at the surface of the Earth has the same acceleration due to gravity. So this next question asks if a tennis ball obeys Newton's third law, meaning that if the tennis ball is being pulled by Earth, the gravity of Earth, then that means the gravity of the tennis ball is pulling on the Earth. So the Earth pulls on the tennis ball. Newton's third law says the tennis ball should be pulling on the Earth. Now the question is, why do we not see the Earth accelerate? Because the tennis ball obviously accelerates. So why doesn't the Earth accelerate? And the reason behind that is because the Earth's mass is so huge, it's so big, that the amount of acceleration it would actually have towards the tiny tennis ball is so small that we would never be able to actually observe what that acceleration would be. And in class we actually calculate what this acceleration is that the Earth would be accelerating towards the tennis ball. Next example problem says a 90 kilogram man and a 55 kilogram man have a tug of war. The 90 kilogram man pulls the rope such that the 55 kilogram man accelerates at 0.025 meters per second squared. What force does the rope exert on the 90 kilogram man? Well, we have the mass and we have the acceleration of the 55 kilogram man, so we can figure out actually the force on the 55 kilogram man. So we got this guy over here, 55 kilograms. He's accelerating to the right at 0.025 meters per second squared. Then we got the 90 kilogram guy over here that's also pulling on the rope. Now because they're both pulling on the rope, they both have a force in tension on the rope. And the rope is pulling each one of these guys. So first of all, you got this guy that's being pulled to the right, this guy that's being pulled to the left. And both of these forces are actually going to be equal because the tension in the rope is going to be constant throughout. We use Newton's second law in order to determine the net force that's being applied to this first guy. If the only force that's being applied to him is the force in the rope, then that's going to be equal to the mass of the guy times his acceleration. That gives us 55 times 0.025, and the force that's being applied to this guy is 1.375 newtons. Now that's the force being applied to the 55 kilogram man. Now since these two forces are equal and opposite because of Newton's third law, then the force being applied to the 90 kilogram man is going to be negative 1.375 newtons. So next the question is, what is the acceleration on the 90 kilogram man? Well, we have the force that's being applied to him. We figure that out to be negative 1.375 newtons. And the reason this is force 2-1 is because it's the force of the second guy by the first guy. This is force 1-2 because it's the force of the first guy by the second guy. And these two forces are equal and opposite as we used Newton's third law in the previous slide. So we have his force and we have his mass. We can use Newton's second law where net force equals mass times acceleration. Well, the only force acting on this guy, assuming there's no friction with the ground or air resistance or anything like that, is going to be force 2-1. And that's going to be equal to the mass of this guy times acceleration. So we plug in our numbers. We got negative 1.375 is going to be equal to 90 times acceleration 2. We divide both sides by 90, and we get the acceleration is going to be equal to negative 0.0153 meters per second squared. And hopefully that kind of makes sense because his acceleration is going to be in the negative direction where the acceleration of the first guy was in the positive direction. They're accelerating in opposite directions. But you should notice that the accelerations are not the same. Newton's third law says each force is going to be the same and equal and opposite, but not the accelerations. So if the 55 kilogram man has a 0.025 meter per second squared acceleration, then the 90 kilogram man with more mass should have a smaller acceleration. Indeed, that's what we get in this example. Let's do a few example problems first. A raindrop with a mass of 2.45 milligrams falls to the ground. As it is falling, what magnitude of the force does it exert on the earth? Now we can't really figure out the force that it exerts on the earth, but we can figure out the force that the earth exerts on the raindrop by using Newton's second law. Newton's second law says net force equals mass times acceleration. Now the only force acting on the raindrop is the force of gravity from earth, and that's going to be equal to the mass times acceleration. Now this mass is originally in milligrams. It needs to be converted to kilograms, so we divide by a million, or divide by 10 to the 6, and we get 2.45 times 10 to the negative 6 kilograms, and multiply that by the acceleration. Now anything that's falling on Earth with no air resistance is going to have an acceleration of negative 9.8 meters per second squared. So we can plug that in for the acceleration. We get the force that's going to be applied to this raindrop is negative 2.401 times 10 to the negative 5th newtons. Now that's the force that the Earth is applying to the raindrop. In order to figure out the force that the raindrop is applying on the earth, we can use Newton's third law. Newton's third law says for every force there's an equal and opposite force, equal in magnitude, opposite in direction. So since the force being applied to the raindrop is negative 2.401 times 10 to the negative 5th newtons, the force being applied to the earth is going to be positive 2.401 times 10 to the negative 5th newtons. Now we can use this right here in order to determine what force Earth is going to put on everything that is on it. And this force of gravity is actually a term that means weight. This will give you the weight of any object. So in order to determine the weight of an object, you simply take the mass and multiply by the acceleration due to gravity, because that's the acceleration that gravity is wanting to accelerate everything at. So the weight of the object is going to be equal to the mass of the object times 9.8, where 9.8 is going to be g, which is that acceleration due to gravity at the surface of the Earth. Now we're going to look at how to create a free body diagram. First thing you have to do when you have something that has forces acting on it, you have to choose what your system is going to be. Now this example right here, I've got this bucket. I'm going to say this bucket has is going to be my system right here. And as you can see, there's a contact force with this bucket. There's the force of tension pulling upward. But there's also a field force, since I'm dealing with the surface of the Earth, and the field force has gravitational force downward. So the positive direction we're going to say is upward, and then the negative direction is going to be downward. And then we locate the contacts with our system as well as the field forces acting on our system. Now the most common field force we're going to be dealing with is the force of gravity. So we draw our free body diagram where we say our system is going to be this dot right here. And then the forces that are acting on my system, I got force of tension upward and I got force of gravity downward. Now let's suppose I have this system where the velocity is increasing in the upward direction. If the velocity is increasing upward, then that means velocity being upward and it's increasing, then the acceleration has to be in the same direction. So the acceleration is upward also. If the acceleration is upward by Newton's second law, that means the net force is upward as well. If the net force is upward, then the upward force has to be bigger than the downward force. So force of tension actually has to be bigger than the force of gravity. So going through this again, velocity is upward and velocity is increasing. That means acceleration has to be upward. If acceleration upward by Newton's second law, net force has to be upward. If the net force is upward, then the two forces that are acting on it, the upward force of tension, the downward force of gravity, the upward force of tension has to be bigger in order for the net force to be upward. Now these problems right here, these are all examples that we do in class in order to basically run through the same scenario we did in the previous slide. So to run through this again, we say we have a water bucket that's being lifted by a rope at a decreasing speed. So the first thing we're going to do is we're going to identify our system and we're going to draw a free body diagram. Our dot represents our system, and then we have our forces acting on it. We have an upward force of tension from the rope and a downward force of gravity. The tension we know is there because it's a contact force. Gravity we know is there because we're on Earth and gravity is going to be pulling down as long as we're in the gravitational field. Okay, so it says that the bucket is being lifted, so the velocity is upward, and it says that it's decreasing in speed, so that means the acceleration has to be downward. If you remember from Unit 1, when acceleration and velocity are in opposite directions, objects slow down. When they're in the same direction, they speed up. So since the object is being lifted, moving upward, and it's decreasing in speed, then that means the acceleration has to be in the opposite direction, which is downward. By Newton's second law, if the acceleration is downward, that means the net force has to be downward. Well, if the net force is downward, that means the downward force has to be bigger than the upward force. So the force of gravity is going to be greater than the force of tension. So some misconceptions to deal with as we go through this class. First one is when a ball is being thrown, the force of the hand is throwing the ball remains on it the entire time while it's moving. The reason this is a misconception is because the hand being applied to the tennis ball, whatever it is a contact force. So when it's not in contact anymore, that force is not being applied. Now that refers to Newton's first law. An object will continue moving with no force being applied. So you don't need a force in order for it to continue moving at a constant velocity. Now that brings us to our next one. It says a force is needed to keep objects moving. A lot of times we think that objects have to have a force to keep moving. This may come from the fact that, you know, when we're driving in our car, we have to keep our foot on the accelerator in order to remain at a constant speed. Now, it kind of makes sense that you need a force, but really what that force is doing, it's not keeping you moving. That force is actually balancing the air resistance that's trying to push against you. And because those forces are balanced, then you can move at a constant speed. If those forces are not balanced, you're going to accelerate, you're going to speed up or slow down. The next misconception is inertia is a force. Inertia is not a force. An object will continue moving without a force being applied to it. The inertia of an object is essentially how much an object resists change, and it has to do more so with mass than force. The mass of an object and the inertia of an object are very closely related. The more mass an object has, the more inertia it has, the harder it is to get it to change its motion. But inertia itself is not a force. And the last thing is that air resistance is not a force, or air does not exert a force. And this is actually a misconception because a lot of our examples that we're going to be doing, we're going to say, quote unquote, that air doesn't exert a force. There's no air friction, or you can ignore air friction. But in fact, in a lot of examples in real life, we do have a lot of air resistance. We're just trying to simplify in physics, simplify our equations a little bit by not talking about air resistance yet.